me if you think this or wicked hot. Those are the only options that I'll accept.
All right. I'm going to take my microphone. I'm going to hold it right over the top so you can hear what's going on in here. All right. So Emily, does anybody have any thoughts out there? Super cold or wicked hot?
I do have some really cool thoughts. I see a lot of people, most people saying super duper cold. I'm also seeing someone saying wicked cold. And I do see one comment that says hot question mark. So there is some uncertainty out there.
Well, this liquid, it might remind you of water here that made you think, goodness, that must be cold.
Well, it's hot because it seems to be boiling, but I'll keep looking for other responses. Oh, someone is noticing a fog, or they're also calling it a smoke thing coming out of the top of the container. Someone says that the vapor is moving down instead of going up.
Perfect. Yeah, those are all great observations. Okay, so it might be cold stuff, but someone thought from a liquid to a gas.
And remember, you guys can put your predictions into the Q&A box. What do you think will happen to that rubber stretchy band when it comes out of the liquid nitrogen? All right, so someone is thinking that it will shrink in size. Someone else is thinking it will freeze and harden.
All right, those are great ideas. So we know that, all right, our liquid nitrogen's minus 320 degrees Fahrenheit. Our rubber tube was almost 70 degrees Fahrenheit. We know the temperature of the rubber tube is going to lower, right? It'll be pretty low when it comes out. But let's see how it physically changes. Can you hear that? Doesn't sound soft anymore, does it, friends? Yeah, and I can't stretch it either. So the part that was in my hand that's still toward room temperature, you can see, is pretty stretchy still. But the section that was in the liquid nitrogen is no longer stretchy and bouncy. It's actually rigid and feels like kind of brittle. What do you think is going to happen if I add heat? If I warm this rubber tube back up? All right, let's find out. I'm just going to stick it right underneath my armpit here.
I do have a prediction, Janine, that it'll go back to its original shape, possibly. It will loosen. Let's see, maybe it'll become soft again.
All right. I'll tell you, this feels rather refreshing. I've stuck it right underneath my armpit. I'm using my body heat to add heat to our rubber tube. And let's see what's happening to it. See, it's back to its pretty much stretchy, bouncy self. Okay, so our rubber tube, became kind of brittle when it lost heat to our liquid nitrogen. Rubber has these long molecules that can kind of slide by one another at room temperature. But as the temperature drops, those molecules get closer together. And as they get closer together, they can't move by one another as well. And rubber becomes really brittle and actually can crack and break. Now you might be thinking, who would care what happens to rubber when it gets that low? Well, the transition for rubber to become brittle like that is right around minus 10 degrees Fahrenheit. And you can think about places on planet Earth that humans go regularly, even like you think a really cold winter day here in New England, rubber tubes on cars, tires, these things can start to behave differently. And engineers need to think about how the materials they're using will change with temperature and make sure they're still going to behave in a way that's safe for their intended use. So yeah, it is kind of amazing the things that can happen to different materials when they lose heat. All right, so that was a solid thing. Let's check out a liquid thing next. I'm going to take two balloons that are filled with liquids. The blue one here, I'm putting right in front. This one's filled with water. everyday wonderful liquid water. The red one is filled with a liquid called glycerin. It's kind of a sugary liquid. It pours a lot like maple syrup, very thick and viscous. So we're going to put both of them in here. While I'm doing that, I want you to watch closely to all the changes that you can see and also make a prediction about what you think is going to happen to the two liquids. So here we go. There's the water. There's the glycerin.
All right, and folks, let me know what you think will happen to those two different liquids inside of those balloons. I also want to share a light bulb moment that one of our watchers had, which is that you can take heat out of an object and then also add heat back to that object.
Okay,
if you so desire. So someone is thinking or maybe hoping that there will be an explosion.
Explosions are great.
Maybe the water will freeze. Maybe one of them will turn into like a slushy kind of, what is that called? Material. Maybe it'll get bigger. Maybe the red one specifically will blow up.
Awesome. These are great ideas. All right. Now, I always feel like I'm cooking a little bit when I'm watching this happen because I kind of have to wait a moment. And while we're waiting, you might notice all of this steamy stuff at the top. And like when nothing's in our liquid nitrogen, there's pretty much none of it. But as soon as I drop something in there, we get lots of bubbling, lots of boiling, and the steamy stuff reappears. Well, remember, everything I'm putting into liquid nitrogen is pretty much at room temperature. And the heat from those objects is causing our liquid nitrogen to boil. And as it boils, it changes to a gas. And as it changes to a gas, some of it kind of starts to come out here at the top and interact with the air in the room around it. And the steamy stuff we're seeing is actually water vapor, condensing water vapor, little tiny, 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 tiny droplets of water. You can think of it like a cloud. Okay, I think we're ready to get these balloons out and see what's happened to them. Because I think I heard a pop. That's the water. Here's the glycerin. You can hear they're both frozen solid. When we use the word freezing in science, we're talking changing from a liquid to a solid. So we definitely have solids in here. If we take a good look at our blue balloon, you might be able to see the ice sticking right out. It's just poof, popped open. The red balloon with our glycerin, no holes, no breaks, no cracks. In fact, it's smushed up just a little bit. It's kind of dimpled. Yeah, the glycerin does what most things in the universe do. When they lose heat, the molecules tend to get closer together. As they get closer together, the overall size of the thing gets a little bit smaller. Water is weird, wonderfully weird. When water molecules start to lose heat, at first, yeah, they get closer together. But then, as they get close enough, one side of the molecule and the other side of the molecule, one side's a little bit positive, the other side's a little bit negative. And just like magnets you might have played with before, they can push and pull on one another. And as they get close enough together, they actually push away from each other enough, just that they take up more room as a solid compared to liquid. It's a wacky, weird thing about water. Water's, yeah, one of the few things in the entire universe that does that. All right, so we're gonna put that aside. There's our water. There's our glycerin. So we saw a solid thing, liquid things. Let's check out what happens to a gas when it loses heat. Before we all got here together today, I spent some time blowing up balloons. And I've got about 10 of these balloons right over here to the side. And I'm wondering, how many do you think I'm going to be able to get in here? So if you put your prediction right in the chat box, they're all about the same size. What do you think? 3, 4. Okay, I'll start putting them in. And we'll see what happens.
So we do have a prediction that only 4 or 5 will fit in there out of the 10 that you have blown up. Maybe 3, maybe 7. I do see one single person thinking that all of them will be able to go inside of that container.
Nice. All right, let's watch carefully what's starting to happen.
Oh no.
It's okay. Let's use our liquid nitrogen here. I'm going to pour some right over the top. And yeah, I got them all in. All right, so we've got all 10 of them in there. And as you're looking at our balloons, you can see, wow, they're taking up a lot less space. All right, so the question I have for you is, what has happened to the air inside the balloons? Yeah, so put some ideas in the Q&A. Emily will share what your thoughts are, and I'll keep watching the balloons. See what I can see.
So I'm just waiting for some responses to come in. What do you all think happened to the air inside of those balloons? So one person is thinking maybe they all popped. Maybe the balloons popped, so now the air has escaped from them.
Yeah, that's definitely a good idea. You know, when balloons get smaller, we think, okay, there might be a hole. And we did see rubber got really brittle. And the outside of the balloons is a lot like our rubber tube. The outside of the balloons, let's take a listen. I'll take my microphone and hold it right over the top. You can hear they sound pretty crunchy. Okay, so maybe the material of the balloons is like cracked in their holes.
Yeah, I have a lot more people saying that maybe somehow the air got out of the balloons. I do have one person saying that maybe the air itself got smaller.
Yeah, we were just talking about things changing size. We had water, which, you know, was able to take up more space. But remember, I said most things take up less space when they lose heat. So maybe the air inside the balloons is just taking up a lot less space as it's lost heat to our liquid nitrogen. Now, there's a way for us to check this out, get some evidence in one way or the other. As I take these balloons back out and put them on the table, they'll be in the room temperature air out here with me, and they'll gain heat. As they gain heat, well, if they've got holes in them, they'll be just little flaps of rubber with holes in them. If they've somehow, the air is still in there and it's just gotten smaller, well, we should be able to see that as well. All right, so here we go. I'm going to use my spoon, pull these out. And I use my tongs here. Things are getting, there we go.
All right, so I have some great predictions coming in that they were going to kind of reform and go back to their normal size. I have an observation that they are getting bigger.
Yes.
And expanding.
Great job. Yes, you can see our balloons are returning to their original size. The air was in there the whole time. So we're taking a little bit longer than other, and that's okay. Got one over here. Okay, so those air molecules inside the balloons, when they're at room temperature, they're moving around more, right? Taking up space, pushing on the sides of the balloon. And as we put them in with the liquid nitrogen, those air molecules lose heat and the temperature goes down and those molecules move less. As they move less, they get closer together. As they get closer together, they push on the sides of the balloon less and the balloon around them collapses. This is amazing. We can do this over and over again. It doesn't matter what kind of gas it is. Here we've got air, but it could be nitrogen, it could be argon, it could be helium. Any gas, this happens to. When that gas loses heat, the molecules get closer together, the gas takes up less space. So volume, how much space the molecules take up. Their temperature, how much those molecules are moving around. And the pressure, how much those molecules are pushing on things around them, are all related. Volume, pressure, and temperature. for any kind of gas. It's kind of a cool thing. Check it out. I do this again and again. All right, we'll put our balloons to the side. And we've got one more experiment for us. Emily, have there been any questions or comments?
I mean, tons of really excited comments about all of these experiments. I did have one question about whether we use liquid nitrogen in everyday life, like for air conditioning or refrigeration.
Yeah, liquid nitrogen is pretty special stuff. It's hard to store. So you'll see it sometimes in medical settings. Doctors and nurses will use it. I've had family members had pieces of like moles removed or other skin things. They'll actually put the liquid nitrogen on their skin, and that causes the skin to start to, lose heat and actually sort of be easily to come off. So that's one place you'll see it. Another place you'll see it is like in industry. Lots of industries will use liquid nitrogen to cool things down quickly. And of course, science. We love using liquid nitrogen for science demonstrations. But even people who are doing experiments in different kinds of research labs will use liquid nitrogen to store samples, to change the temperature of pieces of material that they're testing for one thing or another. So yes, in our everyday life, there are uses for it, but not just for your refrigerator or for your like everyday home use. It's very difficult to store. And since it's at such a low temperature, it can be really dangerous if you don't know how to handle it properly. Great question. All right. So I said at the beginning, we were going to see a material change properties just as it changes temperature. And what I'm going to do is I'm just going to bring my setup forward here. And we're going to zoom in as I tell you what we're looking at here. This whole thing is really small. But what I'm holding looks like a small, tiny hockey puck. This is a material, you could think of it, it's a bunch of different chemicals all baked together till it's hard. We can kind of classify this as a ceramic, like your coffee cups at home are ceramics. I'm going to put this right here. I also have a very tiny cube. I'm going to put the cube inside my tweezers so you can just see how small it is. The cube is a magnet, very small, but very strong magnet. I'm going to put the magnet to the side. And what I'm going to do next is take our liquid nitrogen and pour it over our ceramic. Well, first I'm going to put, just so you can see what this does at room temperature. Nothing exciting. So right now I've got the magnet sitting on top of the ceramic. We're going to take that off. And now I'm going to take my liquid nitrogen, pour it right over the top. And as I'm doing this, you're going to see lots of bubbling, lots of boiling, lots of that condensing water vapor. And what I'm waiting for is for the bubbling to mostly slow down. Because I know at that point, my ceramic and all the materials around it are almost the same temperature as liquid nitrogen, somewhere minus 300 degrees Fahrenheit. Okay, that's probably good. I'm going to reposition my ceramic. It's right in the middle. And I'm going to pick up my magnet. I'm going to put it right over the top. And I want you to watch closely. Here we go. 3, 2, 1. Oh, got pushed off.
Wow.
All right. Whoop. It got pushed off again. So if I can get it to stay, I'm going to put a little more liquid nitrogen on here and get that temperature a little bit lower.
And when Janine gets this going again, everyone, I just want you to try to look for the spin that magnet is doing.
All right, I'm going to reposition. Just kind of moved off to the side here. There we go. I've got my magnet. I'm going to put it right over the top. I'll give it a little spin. objects. And I've got my loop here, so you can see there's no strings, no wires. That magnet is just floating, hovering right above our ceramic. Now, we all know that gravity is still working in this room, pulling objects down to the mass of planet Earth. But something's pushing back here. That ceramic underneath, we call a superconductor. Now, you've probably heard the word before, conductor. Conductors allow electricity to move through them easily. Superconductors do it super. That means that electric charges can move through with almost no resistance. What's this got to do with a magnet? Magnets and electricity are always connected. Where you have one, you have the other. So as the magnet is sitting there above our superconductor, the superconductor becomes a magnetic mirror, meaning that if our magnet is making a south pole, our superconductor also makes a south pole. And if you have two south poles, what do? Push away. If it makes a north pole, it makes a north pole. And they also push away. So that's what's pushing our magnet up in the air and keeping it where it was. And as it warms up, as it gains heat, this superconducting property goes away. Superconductors only work at really low temperatures. It's kind of weird. At normal temperatures, they don't have this property. At low temperatures, they do. And scientists have been investigating different combinations of materials to see, well, what temperature do they start superconducting at? And they've been doing research to try to figure out, can they get that temperature closer and closer to more normal temperatures? Because if they could, they can think about different technologies. You could think about different technologies that we might be able to invent that take advantage of electricity being able to move from one place to another without any losses. Yeah, this is one of the coolest things I think I've seen in a while. I hope you enjoyed this demonstration here. I'm curious what you're thinking, what you're asking about, what you're wondering. Emily, does anybody have any thoughts they've put in the Q&A?
I haven't seen any new or pressing questions, just a lot of things saying, that's amazing, wow, wow, wow. We even had a whole classroom with us today that have just been hanging off of every word and every experiment that you've done today. So awesome job.
Oh, thank you. I will say, I just read an article about a new superconductor that uses yttrium and hydride. And that combination is one of the highest temperature superconductors that humans have been able to create at this point. But it also requires something else. So they changed the temperature. They also changed the pressure. They pushed on it really hard. And that's how they got the temperature of the superconducting not to be so low, is by increasing the pressure. So that's kind of an interesting idea, that the pressure and the temperature for these solid objects are connected. If you remember back to our balloons, the air, remember the pressure, how much they're pushing on things around it is related to the temperature as well.
Cool. Thank you, Janine. I guess I have one more question that just came in. Someone is wondering if they can do anything like this superconducting at home.
That would be awesome. There are some amazing things you can do with magnets. If you have access to magnets, just even everyday normal magnets, you can start playing with them in different ways and see how they move compared to one another. Now, I will say superconducting material is not something that all of us have access to, and a liquid nitrogen certainly is not something all of us have access to. But just being curious about how things behave when they change temperature is a great way to explore your world. Even if you just have a freezer, there are lots of experiments you can do with your family and friends. Just make sure you always ask permission before you start doing experiments within your house. But yes, I definitely encourage people to do experiments with temperature, whether heating things up or cooling things down, because you can learn a lot about the world around you exploring that way.
Awesome. Thank you so much, Janine. Do you want to say goodbye to the audience now that we're officially out of time?
Okay. Thank you, everyone. Have a great day. Thank you for joining us.
And folks, thank you so much for joining us as well. I'll say my goodbye as well. I love seeing your participation in that Q&A box. Thank you for all of your questions and comments throughout the entire program. If you're interested in seeing any more programs like this, you can go to our website at mos.org/MOS at home. And if you really enjoyed this presentation, please consider visiting engage.mos.org/welcome to make a contribution. So thank you all so much again, and hope you have a great rest of your day, and we'll see you again next time.